Okay, so this is my attempt of the AP Calculus BC 2024 FRQs. The scoring guidelines have not yet been published, so this is just my attempt. If I make mistakes, which is definitely possible, please do point out in the comments so that our fellow learners can be aware of any mistakes that I make. Um, okay, let's get started. So the first part is the calculator section, I believe. Yep. Okay, so we have that the temperature of coffee cup at time t minutes is modeled by a decreasing differentiable function c, where c of t is measured in degrees Celsius. Okay, so it's what we do know. I like to just take whatever I see in words and turn that into into symbols that I can, do math on. So we see that there's a decreasing differentiable function, which means that we have c prime of t is less than 0. So it's decreasing. Okay. And c of t is measured in degrees Celsius. Okay. Between 0 and 12 seconds, or rather minutes, because the table shows that it's in minutes. Between 0 and 12 minutes of time, selected values of c of t are shown in the table above. Okay. Approximate c prime of 5 using the average rate of change of c over this interval from 3 to 7. Okay, so this is just a finite difference, right, that we're going to write out. And this is just the slope formula. So c prime of 5 is approximately the rate of change of c from 3 minutes, to 7 minutes. So we have, I'm just going to underline that was the wrong one to underline. I'm going to underline the relevant points to choose, so 3 and 7. So this is going to be approximately, actually, you know what? Should I write it out? I'll write it out, and then I'll put it in my calculator. You know what? No. Why would I write it out? You can see it as I'm typing it in my calculator. So I'm not even going to write it out here. I'm just going to do it in my calculator um, and assume that you can read my calculator. I'm going to make sure that you can see my screen, but um, let me see. Here's my calculator. Excellent. You can see it. So we're going to look at C of uh, C of 7 minus C of 3, so 69 minus 85. So I'm just going to put a fraction in here. So it'll be 69 minus 85 over 7 minus 3, right? Because we have C of 7 minus C of 3 over 7 minus 3. So this is just the slope formula, which is a finite difference. And our solution we get is -4. That tells us that, so again, I'm not showing all my work here, but everything that I'm doing in my calculator is the work that you would include. But just for the sake of, because I'm trying to write with my fingers on my screen, so it's just a little bit ugly, but hopefully you can bear with that. C prime of 5 will be -4 approximately. Now we're going to do a left Riemann sum with 3 subintervals with the data given to approximate the value of this integral. Okay, so that integral from 0 to 12, we're going to use a left Riemann sum. So when we think about left Riemann sum, so let's say this is my function, I'm going to choose the left endpoint and then times the width of this interval, right? So this height times this, then this height here times this, and then this height times this. So these are my left endpoint. So that means I'm going to choose C of T star, where T star is like the height of that left endpoint, and then times that interval. So that means I'm going to choose 100, 85, and 69, right? So I'm going to do 100 times the interval, which is 3 minus 0, which is 3, plus 85 times 7 minus 3, which is 4, right? So because the length of that interval is 4, so that's like my x times the y, which gives me the rectangles areas, and then 69 times 12 minus 7, which is, oh, I did that wrong, didn't I? No, I did that right. 69 times 12 minus 7, which is 5. Okay, so let's see, we get 985. That means this integral is approximately, oh dear, 985. Again, Excuse my bad handwriting. Okay. And then this integral would then be approximately 985 over 12, which is approximately 82.083. So 82.083. And what that tells us, so when we say interpret the meaning, again, I'm not going to write this out. I'm just verbally going to explain it. But what that means is that, remember, this is actually from the mean values theorem, right? When we have the integral from a to b of f of x dx over b minus a, this is the average value of f on that interval, right? So that's what the mean values theorem tells us. So this is like the second version of the mean values theorem. The first version of the mean values theorem has to do with the average rate of change over an interval, and the fact that there must be if you have a continuous and differentiable function on that interval, you must have a point whose instantaneous rate of change is the same as the average rate of change on that interval. But this is the mean values theorem for integrals. And what this tells us is that the average temperature of the coffee cup is 82.083 degrees Celsius from 0 to 12 minutes. Okay, I believe that should earn you full credit if you say it like that, is that the average temperature of the coffee cup, the average temperature of the coffee in the cup is 82.083 degrees Celsius, approximately, of course, right? In the interval from 0 to 12 minutes. Okay, now for 12 to 20 minutes, the rate of change is modeled by this function here. I'm actually going to erase some of this g here because it's writing over that. But we have this c prime of t here, and c prime of t is measured in degrees Celsius per minute. We want to find the temperature of the coffee cup at C of 20. So that means we want to find C of 20. So at any time we're given a derivative and we're asked to find the value of a function, we're going to have to use the fundamental theorem of calculus, right? So C of 20 is going to be C of some initial value, and this is valid from 12 to 20, right? So why don't we just use the 12, the value at C of 12, because that's given in the table, right? So we're going to use C of 12 plus the integral from 12 to 20 of C prime of t dt. So what this is saying is that we're starting at C of 12 and we're accumulating some change, which is given by the integral of C prime of t, right? Because this integral is delta C. It's a change in the temperature over that interval, right? So that's our setup, and now we're just going to put this in the calculator. C of 12 is 55 plus, and then we're going to take the integral from 12 to 20 of C prime of t dt. Then we take the integral from 12 to 20 of C prime of t dt, but C prime of t is negative 24.55 times exp of 0.01 t divided by t dt. And that should be good, negative 24.55. I just want to double check that I typed in everything correctly. It looks good. So if I've typed in everything correctly and I've done the math correctly, then 40.329 is my solution. So this is approximately 40.329 degrees Celsius. Make sure you include the units. I should have included the units here as well. Right, so that should be degrees Celsius times seconds. Maybe they don't care so much about the units. I'm not sure. But just to make sure, C prime of 5 is negative 4 degrees Celsius per minute. Well, actually, I guess if you're defining C of t as a number rather than as the actual temperature, then you can just write negative 4. So maybe they don't actually expect you to include the units, but I just thought I'd bring them up because that way you kind of have intuitive understanding for what these numbers mean. So again, you don't really need to include these units, I think. But yeah. Yeah, but so here though, the reason I would include units is because they ask you to find the temperature of the coffee, not the value of C of 20, right? I mean, they're the same, they're representing the same thing, but C of 20 is the temperature divided by degrees Celsius. It's a number, right? Whereas if it asks you what is the temperature, then you should write up the actual temperature, in my opinion. Okay, and for the model defined in part C, it can be shown that this is the derivative of C prime, okay? And then for this interval, determine whether the temperature is changing at a decreasing rate or at an increasing rate. Well, okay, so in this interval from 12 to 20, no matter what we plug in, you see, C double prime of t will be bigger than 0 because an exponential is always positive. This is positive. T squared will be positive. So 100 minus t is the only thing. And whether I plug in 12, whether I plug in 13, whether I go all the way up to 20, all of that will be positive. So C double prime of t is bigger than 0 for 12 is less than t is less than 20. What that means is that C prime of t is, what would that mean? It's increasing, right? So C prime of t is increasing, right? So what that means is that even though C prime of t itself is negative, right? Because we started with 55 degrees Celsius and then we went down to 40 degrees Celsius, which makes sense because, right, we already mentioned in the beginning that C prime of t is less than 0. It's decreasing, but the rate at which it's decreasing is increasing. Hopefully that makes sense. So in other words, it's decreasing, but it's concave up. So what would that look like? It's decreasing, but it's concave up. Oh, now this is an interesting question. C prime of t is increasing. This is a true statement. Now, this is kind of I'm not sure exactly what they mean by this wording. So I have a picture for so the C of t would look something like this, but the rate at which it's decreasing by magnitude is actually, by magnitude, it's actually decreasing. So by magnitude, maybe you could write this. By magnitude, C prime of t is decreasing, but by value, of course, C prime of t is increasing. So I'm not sure when they use this verbiage here, whether they're referring to the magnitude or whether they're referring to the actual value of C prime of t, right? Because C prime of t, as we saw, was negative. Sorry. No, that's right. C prime of t is negative, which means C is decreasing, but C double prime is positive, which means that C prime is increasing. So it's negative, but that negative number is getting closer and closer to 0, basically. So by magnitude, the rate is decreasing, but by value, C prime of t is increasing. So that's the best I can do. I don't know what they're looking for here. And my reason, of course, is because C double prime of t is bigger than 0 on this interval. You can, of course, plug in the endpoints and show that from 12 to 20, which is an increasing function, if you just use the endpoints. So what I mean is that 100 minus t is a decreasing function, right? As t increases. So if you have within those intervals, if you test both of those endpoints and they're both positive, then that means it's positive on that whole interval. So you can write that out fully if you want. You probably should. I don't know what's required by the exam people. Okay, so number 2. This is going to be a parametric problem. Particle is moving along the curve in an XY plane, has the position X and Y, where X, okay, blah, 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 they're in centimeters. So X prime is given by this, Y prime is given by this, time t equals 2 seconds, the particle is at this point. Find the speed. Okay, so remember, speed is the magnitude of velocity, right? So if speed is the magnitude of velocity, we just have that speed equals the square root of x prime squared plus y prime squared. It's like Pythagorean theorem, right? Because that's where, if you have the picture of the vectors, right? If you have the pictures of the vectors as x prime and y prime, then you can think of it as speed is the length of that hypotenuse. Okay, so we want to find the speed at 2 seconds. So that's our setup, and then now you can just plug stuff in. In fact, what I'm going to do actually is I'm going to define some functions in my calculator that will actually make it easier. I'm going to define a of t as x prime, which is 8t minus t squared. And then I'm going to define b of t as y prime, which is negative t plus the square root of t to the 1.2 and then plus 20. Hopefully I've typed this in correctly. That's the biggest risk with all of this is just the calculator problems is did you type in stuff properly? I think I've done everything properly. Okay, good. Um, so we want to find the speed. So this for the speed, all we're going to do is take the square root of a squared plus b squared, right? But we're going to find evaluate a at t equals 2 seconds. So we're going to take x prime of 2, in other words, a of 2 in my calculator, a of 2 squared plus b. Actually, one thing I will do is I will put parentheses around my a of 2 just because I'm not sure whether the calculator will square the 2 or if it'll square all of a of 2. So I will go ahead and do that. So a of 2 squared plus b of 2 squared. And again, I just don't want to take the risk, so I might as well put that extra parenthesis in there. And that turns out to be 12.305 approximately. So 12.305. And again, it asks for the speed, so I should put the units, which is centimeters per second. Good. Okay. And then find the total distance traveled the particle over. So here's how I think about distance. It's just like arc length, right? So if I have an XY coordinate system here, and here's my path, right? The total distance is the length of this arc. And from arc length, you can just imagine I'm zooming in on this triangle, we have a dx, we have a dy, and then this is dl, right? So from Pythagoras, we know that dl squared has to be dx squared plus dy squared, which means dl is the square root of dx squared plus dy squared. Now, the problem is I have dx dt, so what I can do is I can just multiply this and divide this this right-hand side by dt. And the reason I would do this, now I can pull the dt inside, and now I get x prime of t squared plus y prime of t squared. Okay? So speed was essentially like your speed is actually dl dt if you got it, right? Because what this is doing is this is x prime of t squared plus y prime of t squared, the square root, dt, which allows me now to integrate both sides. But speed is the rate of change of your distance, right? So it's dl dt. That's what we found here. Speed is dl dt, and this right here is actually dl. So now I can integrate that. So if I want, so the total distance would be equal to the integral from 0 to 2 of the square root of x prime squared plus y prime squared dt. And again, this is something you just plug in the calculator. And you see the nice thing is once you define these functions, you don't have to retype them every single time. I'm going to take the integral from 0 to 2 of the square root of a of t squared plus b, again, one thing, that's the other thing I should do. I should put in those parentheses just because, again, I don't want to risk it, plus b of t. Maybe I put too many parentheses. I'm not sure. I think I may have put one too many parentheses, but that's fine. Okay, dt. I believe I've typed everything in correctly, and that looks correct, and it's 15.902. So approximately 15.902 centimeters in that interval. Okay, good. So find the y-coordinate of the position at time t equals 0. So again, this is going to be a fundamental theorem of calculus problem. So if we want y of t equals 0, we need some sort of initial condition, which they give us in the problem. At t equals 2, y is 6. So we have y of 2 plus the change accumulated over that interval. So the thing we have to be careful is that now we're, instead of 0 to 2, we're going from 2 to 0 of y prime dt, right? So that's what we're really doing. So we're taking y of 2 plus the change from 2 to 0. So y of 2, as we know, is given to be 6. And then we're going to take 6 plus the integral from 2 to 0 of y prime. Y prime, again, we defined already as b of t, we can just do b of t dt, right? In fact, I didn't even have to, no, I did have to type this because b of t is y prime, not y. So yes, that is 6. 6 plus the change from 2 to 0 of b of t dt. Okay, which is negative 1.174 approximately. Negative 1.174 centimeters. And again, I don't know that you have to, it just says y coordinates, so you could probably just leave your answer like that without the units because it's not asking for the distance or for the, you know. So yeah, you could probably leave your answer like that. That's negative 1.174. There's a very ugly 7. Let me rewrite that. Negative 1.174. That would be the y coordinate. Good. Okay. And then for t is between 2 and 8, the particle remains in the first quadrant. Find all times t when the particle is moving towards the x-axis. So what does it mean? So again, this is the part where we have to take words and put it into math. So if I say that the particle is moving towards the x-axis, so again, let me just draw this out a little bit. So I have a particle moving around. When is it moving towards the x-axis? So here it's moving towards, and here it's moving towards. So it's not like it has nothing to do with whether, I'm not going to say nothing to do with, but it's not whether y prime is less than 0, right? That's, or whether x prime is less than 0. So, oh, actually, no, never mind. One thing I will, it's in the first quadrant. So let me update my pictures to reflect that. So let's say this is x, this is y. I have a particle that's moving something like this. So maybe it was moving like this. Okay. So now what I said before was wrong. I think the words I used were wrong. It does have to do with whether dy dt or dx dt is less than 0. In this case, because it's asking about moving towards the x-axis, it would be these regions here, right? So even this is moving towards the x-axis. So it's anywhere. So based on our picture, it's anywhere where y prime of t is less than 0. If y prime of t is less than 0, that means we're moving towards the x-axis, right? Because we're in the first quadrant. If we weren't stuck in the first quadrant, then what I said before would be true because moving towards the x-axis could be y prime is bigger than 0, right? And that's why this part is really important. Okay, and we want to find all times in this interval between 2 and 8 when it's moving towards. So in other words, we just have to solve y prime of t is less than 0. This is something I would graph. So this is the reason for my answer. And then the way I would do this is just go to graph and, oh dear, my calculator, my entire computer is starting to give up day by day, it seems. What am I doing wrong? Oh, that's why, because I'm in, do I still have, yeah, I'm not in my Scratchpad. I should have done that for the beginning, but let's go back to document. Yeah, my y of t is gone. My y prime of t is gone because I was in a document, not in the Scratchpad. So yeah, I like to do most things in my Scratchpad. But anyways, because it's gone, I'm gonna have to retype this, but that's not a big deal. So f1 of x is gonna be negative x plus the square root of x to the 1.2 plus 20. I believe that's right. Okay. And we really just care about the region from 2 to 8, right? So from 2 all the way to 8, which is here. So we need to find where this intersects the axis, analyze graph, 0, then do a quick root finding algorithm, and then we get our root is 5.222 approximately. So that means between 5.222 and 8, y prime is less than 0, which means that my interval is that, so 5.222 is less than or equal to, should I say, actually, this is a good question. Should I say less than or equal to, or should I say less than? I should say less than, not less than or equal to. And the reason for that is because at t equals 5.222, y prime is 0, meaning it's not moving towards the x-axis yet. It's in that intermediate value between moving away and moving towards. So 5.222 is less than t, is less than or equal to 8, because 8 is included in this interval, is the interval where the particle is moving towards the x-axis. Good. Okay. So now let's move on to, oh, that was it for the calculator section, huh? Okay, we only had 2 calculator questions. How long do they give you for this? Half an hour. Okay, not bad. Not bad. All right, now let's move on to the non-calculator section. Okay, so the depth of the seawater at a location can be modeled by the function h that satisfies this differential equation. H of t is measured in feet, t is measured in hours after noon. It is known that h of 0 is equal to 4. Okay, h of 0 is 4. That's an initial condition that we're probably going to need. A portion of the slope field for the differential equation is provided. We need a solution curve for h of t through the point 0, comma 4. So it starts here as they give us. I always struggle with these because I'm going to assume it'll look something like this, something like that. I just like to follow the lines. I mean, has to be tangent. Like those are the tangent lines at each of those points. So hopefully I've done a decent job of this. But yeah, it'll look something like that. All right. And I can label that as y equals h of t if I want. Okay. So for 0 is less than t is less than 5, it can be shown that h of t is bigger than 1. So h of t is positive between 0 and 5 and bigger than 1. Okay, find the value of t for which h has a critical point. So remember, what does it mean if h has a critical point? Critical point means that h prime is either equal to 0 or undefined, right? So we're going to see when does h prime equal 0. So dh dt, if we set dh dt equal to 0, that would be, so I'm not going to write all this out, but hopefully you can see. dh dt equals 0 would have to imply that h equals 1 from the zero product property, right? So this would imply that h equals 1 or that cosine of t over 2 is equal to 0. And there's no value that I can think of that would make these undefined unless h is, yeah, h is undefined, but we're going to assume, yeah, they tell us for between this interval, h of t is bigger than 1, but h of t is bigger than 1, so that means this solution goes away. So that means we're only going to look at this. Cosine of 2 over 2 is equal to 0. When does that happen? Well, when does cosine equal 0 on our unit circle? It equals 0 when we have x is when sorry, I'm completely blanking. When the argument of cosine is pi over 2 or 3 pi over 2, or so it's pi over 2 plus any integer multiple of pi, right? So pi over 2, 3 pi over 2, pi over 2, 3 pi over 2, and then 5 pi over 2, and so on, right? So it'll be equal to pi over 2 plus n pi, where n is an integer. Okay. So then, of course, we can multiply both sides by 2 to get t is equal to pi plus 2 pi n, where n is an integer. Now, in this interval from 0 to 5, what would those values be? Well, pi minus 2 pi would be negative pi, so that would not be allowed. So that means the possible values are t is an element of this set, which could be pi. It could be pi plus 2 pi is 3 pi. 3 pi, is that too big? 3 pi is too big because 3 pi is equal to 3.1415 dot dot dot. So 3 times that would be 9, which is bigger than 5. So the only solution that lies in our interval is t equals pi. So I could have just written that. T equals pi for 0 is less than t is less than 5. So that means t is equal to pi. Let me just make sure I've done that math properly. T over 2 has to be pi over 2 plus any integer multiple of pi for cosine to be 0. That's right. Seems right to me. So t equal to pi plus 2 pi n. Yeah, that seems correct to me. 3 pi is too big, as we said, and pi minus 2 pi would be negative pi, which is below 0. So t equals pi is the only critical value. And then or that's not the critical, yeah, that's a critical point. And whether that's a relative minimum, maximum, or neither. Well, this makes the graph here makes it look like it's a relative maximum. So I'll write that down. What we really need to do for that is we need to look right before and right after. Um, yeah, because cosine of any like a number right less just before pi would be would be positive and right after would be negative, right? So you can use that argument that it'll be positive before, then it'll be negative after, right? So that shows, but also I think another reason is you can just show that around pi 3.14, you have a relative maximum in your graph here. So that's another reason you can give based on slope field. So maybe they have multiple slope field. Maybe they have different answers that they will accept there. Okay, so now we need to just solve this differential equation. So this is what it's going to take some space up. I apologize. I'm just working this out on my laptop, but yeah, we have dh over h minus 1, right? So from here, I can directly divide by h minus 1, multiply the dt on both sides to get 1/2 cos t over 2 dt. And I actually like to integrate um, using my bounds. So I like to get definite integrals actually. So I'll do 1/2 cos t from 0 to t. And on this side, I'm going to integrate from h of 0 to h of t. Okay, so on the left side, I get the natural log of h minus 1, or the natural log of the absolute value of h minus 1, rather. And I'm going to skip a step here. Hopefully you can just follow along here. It'll be natural log of h of t minus 1 over h of 0 minus 1, right? Because when I subtract logs, it's the same as dividing inside. And on the right side, I'll get sine of t over 2. So again, I'm doing this in my head, but you could, if you need to write out a u substitution, you can. You let u equal t of 2. Yeah, you would let u equal t of 2. Du would be dt over 2. So then it just becomes that. But yeah, sine of t over 2 evaluated at sine of t, evaluated at t and evaluated at t equals 0. So sine of t over 2 minus sine of 0. But sine of 0 is just 0, of course, so that can go away. So good. And really, that should be 0 over 2. But yeah, that goes away. So now we can solve. We have that h of t. Again, I'm going to do some steps. I'm going to combine some steps just so I can fit it all in one page. But at this point, it's just simple algebra, right? So we have h of t equals 1 plus it would be h of 0 minus 1. So 4. So h of 0 is 4, right? So 4 minus 1 is 3 times e to the power of plus 3 times e to the power of sine of t over 2. I believe that would be your answer. And let me just check. Let's plug in h of 0 equals 4. Plug in 0. Sine of 0 is 0. E to the 0 is 1. 3 times 1 is 3. Plus 1 is 4. So that should be fine. And then, of course, if you really wanted, you can take the derivative and prove it. But I think this is sufficient. H of t is equal to 1 plus 3 times e to the sine of t over 2. I hope I haven't made any mistakes there, because I did kind of skip some steps just because of the space concern. Of course, you can write out more. You have time to write out more as well. But yeah, I think that's sufficient. All right, let's move on to number 4. How many questions are there? 6? Yeah, okay, not bad. So let's look at number 4. The graph of the differentiable function f shown for this interval from -6 to +7 has a horizontal tangent at x equals -2, which means we have a local maximum there based on the graph, and is linear for this region from 0 to here, to 7 actually. So all the way down to the very bottom here is linear. So I'll just annotate my graph a little bit so I I can process that. And then R is this region, the second quadrant bounded by the graph of F, the vertical line x equals -6, and the x and y axes, region R has area 12. So that means the integral of this area, this region is 12. So the function g is defined as the integral from 0 to x of f of t dt. So remember, g of -6, that means we just plug in -6. We're going to get 0, the integral from 0 to -6 of f dt. And the integral from 0 to -6 of f. So here is the only thing that's different. If you go this way, the area would be -12. So this is testing whether you know the properties of integrals, right? If we went from -6 to 0, it would be 12, but we're going in the opposite direction. What about g of 4? Same thing. The integral from 0 to 4 of f dt would be, so going from 0 to 4 would be this area here. So that's just the area of a triangle, which is 1/2 base times height. The base is 4, the height is 2, 1/2 2 times 4. The 2's cancel, of course, we get 4. And then g of 6, again, I apologize. My writing here is an absolute mess, but hopefully you can follow along with what I'm saying. G of 6 is equal to the integral from 0 to 6 of f of t dt. And then from here, we get the same thing, except I can think of this as what I already found, the change from 0 to 4, which is 4, minus or plus the integral from 4 to 6, right? So here, let me write this out. I can think of this as the integral from 0 to 4 of f dt plus the integral from 4 to 6 of f dt. But you have to be aware because the integral from 4 to 6 is a negative value, right? Because it's below the x-axis. So it'll actually be 2 times 1. So 1/2 times 2 times 1 times 2 times, yeah, I'm trying to save space again. But yeah, it'll be 1/2 times 2 times 1. So the 2's cancel, so it's just 4 minus 1, which is equal to 3. So that means g of 6 is 3, g of 4 is 4, and g of -6 is -12. So we have -12, 4, and 3. For some reason, I'm having trouble believing that this is 4, if this is 12. It's not unreasonable. No, it looks okay. It doesn't look too bad. Okay. For the function, so for part B, for the function g defined in part A, find all values of x in the interval from 0 to 6 at which the graph of g has a critical point. So again, if g has a critical point, that means, I'm going to do this up here. That means g prime equals 0 or undefined. So that if g prime of x is 0, so g prime of x, first of all, let's find that using this formula, and that would just be the fundamental theorem of calculus, right? If I take the derivative of an integral, I get whatever function I was taking the integral of, evaluated at the bounds. If it's a function of what you're differentiating over, if that makes sense. And so that would mean that g prime of x is just f of x. Right, so g prime of x is f of x. And that means if g prime of x is 0 or undefined, that means we're asking when is f of x 0 or undefined. And that would just mean if f of x is 0, so the only location where f of x is 0 is x equals 4. And that would be it. And the reason for your answer, I think math is, if you write this out, that is your reason. You can put this in words if you want, but same, you can write a fundamental theorem of calculus by fundamental theorem of calculus. Okay, the function h is defined as this. So h is the integral, I'm not going to rewrite it, it's right there, is the integral from -6 to x of f prime of t dt. So it's the integral from so it's the area, the signed area under the curve from -6 to your current x value of the, oh wait, it's the slope of this graph. So we have to be careful. Often I think it's easier just to write this out. So let's just write it out. H of 6 would be the integral from -6 to 6 of f prime of t dt. So based on the fundamental theorem of calculus, I can just rewrite this as f of 6 minus f of -6, right? It's the antiderivative evaluated at the upper and lower bound. So f of 6 is -1 minus f of -6 which is 0.5. So this would be negative 1.5. So now let's think about h prime of 6. But for that, first I'm going to find h prime of x, which is going to be, again, by the fundamental theorem of calculus, we know that this is just going to be f prime of x, right? Because if I take the derivative of the left side, then I can get rid of the integral. I can evaluate whatever's inside the integral at the bounds, but only if it's a function of, like, if it's, right, because it's ddx of the right-hand side. So that means it'll be f prime of x and not f prime of x minus f prime negative 6, right? So we have f prime of x here. And of course, we can even take it a step back. We know that then we can go and find h double prime here as well, because I know the question is going to ask for it. So h double prime of x is actually going to be something doesn't seem right here again. No, I think I'm doing everything correctly. I think I'm just doubting myself. H of 6, I think I did correctly. H prime of x, I think I did correctly. So then h double prime of x would be just the derivative of that, which is f double prime of x. I think all is looking good right now. So that means that h prime of 6 would be f prime of 6. And we just have to see what is the slope at x equals 6. It's the same slope of this line. Of course, you can show your work, but you can just do a quick little rise over run. So it's negative 1 over 2. So negative half is my slope on that interval. And then f double prime of x is, of course, so if we want to find, let me write it down here, h double prime of 6 would be equal to f double prime of 6, which would be equal to 0, I believe, right? Because it's a linear function. So if I take its derivative once, I'll get a constant function. And if I take its derivative again, I'll take 0. Okay, good. All right, let's look at number 5. We have a function f, which is twice differentiable for all x with f of 0 equals 0. Values of f prime, the derivative of f, are given. For x bigger than 0, the function is defined by this integral. Find the value of h prime of pi. Well, again, fundamental theorem of calculus, h prime of x would just be whatever is inside this function. So 1 over the square root of 1 plus f prime of x squared. And in case, I think they're going to ask you about this later, but this looks awfully a lot like the arc length formula that you should be familiar with. And I'll show you how to derive that real quick, actually. No, we'll do that in the next part. I'll show you how to derive that. But anyways, that's what we get. So that means h prime of pi is equal to the square root of 1 plus f prime pi squared. So we get the square root of 1 plus f prime of pi is 6, so that's 36. So we get the square root of 37, I believe. Looks right to me. Okay, so before I told you about how dl is equal to the square root of dx squared plus dy squared. I showed that to you in the parametric part. So now, how do I get it to match this form? Well, the thing is, I have y as a function of x, so I can multiply this by dx over dx, and I can pull in one of the dx's. If I do that, then I get 1 plus dy dx squared dx. So there you go. This is where this formula comes from. So what information does this provide about the graph of f? This, again, I'm just going to give it to you verbally. I'm not going to write it out because of the space, but that expression provides you with the length of the curve of f from x equals 0 to x equals pi. That's what it gives you. The length of the curve from x equals 0, the length of the curve of f from x equals 0 to x equals pi. Okay. Now we're going to use Euler's method, starting at x equals 0, with two step size of equal size to approximate f of 2 pi. So I like to use the table, as many people do. So we have x here, we have y here. They actually give you f, so let's do it in terms of f. We have x, we have f, then we have f prime of x, right? And then f prime of x is just df dx, so we can multiply, and then we can have if you want. You can have an extra column that's f prime times delta x, right? And again, the idea behind Euler's method is that if I have, what I'm doing is I'm approximating delta f as f prime times delta x. And the reason for that is f prime is df dx. So and we're multiplying by a delta x. So essentially we're canceling these out to get a df. But again, because we're approximating dx with delta x, we get a delta f out. Okay, good. So we start at x equals 0, and we want two step size of equal size to get 2 pi. So we're just going to do pi and 2 pi. F of 0, they tell us what is f of 0. Starting with x equals 0 to approximate f of 2 pi. Oh, they give you f of 0 is 0 here. Yeah. Okay, so f of 0 is 0. F prime of 0 is 5. And our delta x is pi, as you can see. That means our f prime times delta x is just 5 pi. So that means if I do 0 plus 5 pi, I get 5 pi. That goes here. And again, what is my f prime of pi? F prime of pi is 6. So now I do f prime times delta x. Again, my difference is pi. So I do 6 times pi. And then that's how much I go forward with. So 5 pi times 6 is, sorry, 6 pi plus 5 pi. This is, again, my change. So I'm going to add that to what I have. 5 pi plus 6 pi is 11 pi. So that tells us that f of 2 pi is approximately 11 pi. Okay, good. Now we're going to find this integral. I don't know what that has to do with this problem. Maybe they just wanted to throw that in there, but it's here. We're going to take the integral of t plus 5 cosine of t over 4 dt. So we have two functions that are being multiplied. So this is a perfect opportunity to use integration by parts, just because I don't know of any better way to do it. I'm going to use the tabular method of integration by parts. I think actually, if you guys haven't watched it, there's a movie called Stand and Deliver. Jaime Escalante. It's a story of it's about his story. It's a great movie, actually. I think he actually there's a part in the movie where he actually has this tabular method of integration by parts. But essentially, what I'm doing is this is my u, this is my dv, and this just allows me to do it repeatedly, so I don't have to keep writing u's and dv's. I don't know if this is allowed on the AP exam. Probably isn't, but maybe it is. I honestly don't know. So you can do integration by parts your way. I'm just going to do it this way. The derivative of t plus 5 with respect to t is 1. The derivative of 1 with respect to t is 0. Now I'm going to go the other way. I'm going to integrate cosine of t over 5. So that'll be sine of t over 5. But then if I do that, I get a 1/5. So I need to multiply by 5 here. So 5 sine of t fifths, t over 5. I mean, yes, that should work. And then again, got to integrate this to get negative cosine of t over 5 times 25. So now I go diagonally and I multiply. So that means this, I'll write it down here, is going to equal t, I'll write the 5 in the front just for the sake of elegance. 5 times t plus 5 times sine of t over 5 minus, because I have my minus sign here, remember to alternate, minus, and that's a 1 there, so I can just directly have 25 cos of t over 5, or that should be, oh wait, why was I think I messed this up completely. It's not t over 5, it's t over 4. So these are slightly wrong. That'll become a t over 4. That'll be a sine of t over 4, cosine of t over 4 there. That'll become a 4 here, and that'll become a 16 here. And one thing I did forget to do actually here, that'll actually be a plus. Okay, let me just redo this, just for clarity's sake, so that we're all on the same page. Okay, all right. So we have plus, minus, but I don't think we'll need more than that. We'll have t plus 5, 1, 0. We start with cos of t over 4. That'll get us to 4 sine of t over 4, which will get us to minus 16 times cos of t over 4. So that means we multiply this way, we get 4 times t plus 5 times sine of t over 4. Then we do this product, right? So we have a negative here and a negative here, so that turns into a positive 16 cos t over 4. And of course, do not forget your plus c. And there's your answer. Again, I have no idea what this part D has anything to do with parts A through C. Maybe they just wanted to test that in there if you can do a random integral, but yeah, it's there. All right, and here's our most fun question, which is the series question. If I'm going to be completely honest, I've forgotten a lot of the tests that I'm probably just going to search it up so that we can at least do the problem together. But honestly, I don't remember a lot of the tests. But anyways, we have a Maclaurin series given by this. It converges to f for all x in this interval of some interval of convergence. It can be shown that the Maclaurin series has a radius of convergence of 6, and it's centered around x equals 0 because it's a Maclaurin series, right? So we want to determine if it converges or diverges for x equals 6. So I'm just going to plug it in. If I plug it in, I get the sum of n equals 1 to infinity of n plus 1. And I'm not even going to write it out, but if I plug in x equals 6, I'm going to get 6 to the n, and the 6 to the n in the numerator and denominator will cancel. So I'm not even going to write it out, but it'll just be n plus 1 over n squared. I have a feeling this will diverge because it's similar. If you look at the terms, it tends to 1 over n, right? And if it tends to 1 over n diverges. Therefore, I would think this diverges. You might be able to do a direct comparison is pretty easy conceptually, right? Because direct comparison says if I have like 3 over n, of course, 3 over n is bigger than 1 over n for every single n, which means that we know that 1 over n diverges. That's the harmonic series. Or you could do an integral test to show that. Therefore, 3 over n must diverge, right? But this, I don't know if I want to push it. I might be able to do a direct comparison, but I'm not in the mood for that. So I'm going to do a limit comparison. I'm just going to refresh myself over the rules of limit comparison real quick. So actually, here's what I'm going to do. I'm going to pause. Can I pause the recording? Rather than that, let me just search it up on Google or Bing, whatever is on Microsoft Edge. Because Microsoft Edge, of course, does its own thing. Limit comparison test. Let's see. Okay. Limit comparison test. I just need the results. I'll go to images. Hopefully that'll pull something up. I apologize for my computers being extremely slow. Okay. Okay, so if the limit is finite and positive, then either both converge or both diverge. Okay, that's perfect. That's actually what we need. So that means, so if I take the limit as n approaches infinity of my series, my sequence, which is n plus 1 over n squared, I compare it to 1 over n, which I know diverges, then I can take a look at this and go, well, this is going to equal n, the limit, I should have written the limit as n approaches infinity of n times n plus 1 over n squared. And of course, this limit, the highest terms are n squared and n squared in the numerator and denominator. So of course, this equals 1, which is in fact positive and finite. Therefore, diverges at x equals 6 by limit comparison to the sum, or you can just say by limit comparison to the harmonic series, which we know diverges. Okay, good. It can be shown that f of -3 equals this business here, and that the first 3 terms of the series sum to this. Show that this is true. So this is going to be one of those like remainder theorem problems, right? So if I want to show that this is the remainder essentially, right? That is R sub 3, the remainder of the first three terms. That means for the first three terms, what I want to look at is the fourth term. So if I can, so what I do know is that f, the remainder, is bounded by the next term. So it would be the, I don't know how to write this. It would not be f of, it's like if I call this sequence in here a sub n, okay, then I can write it as it's less than a sub 4. Yes, I can do that. Yeah, that's valid. And what is a sub 4? Well, a sub 4, I just have to plug in n equals 4, right? So if I get 4 plus 1 over 4 squared times negative 1/2 to the fourth power, let's see what I get. I get 5 over 16 times, this would be 1 over 2 to the fourth is 16, I believe. And we know that 16 times 16 is 256. So this is 5 over 256, which is indeed less than 1 over 50. And the reason for that is you can, if you need to, you can rewrite 1 over 50 as 5 over 250, just to really highlight that a little bit more. Therefore, we can say the absolute value of f of negative 3 minus s sub 3 is indeed less than 1 over 50 as required. Good. So it's just using the next term, right, as we know. Now we're going to find the general term of the Maclaurin series for f prime and find the radius of convergence for that series. So we have f given here. So I'm just going to write f prime up here. All we have to do is take the derivative of this with respect to x, right? So this is a pretty simple problem. F prime of x then has to be the sum from n equals 1 to infinity of n x to the n minus 1. It's just power rule, right? And remember, this is a derivative with respect to x, not with respect to n, right? So we have that over n squared, 6 to the n. And that's it. Yeah, that's literally it. Nice. That's f prime of x. And now we want to find the radius of convergence. For that, you're going to have to use a ratio test. I believe ratio test is you take the limit as n approaches infinity, and you want to take the next term divided by the current term. So if I take the n plus 1th term of this, I'm going to, on the numerator, I'm going to get n plus 1. Oh, and do you take the absolute value of that? So you have n plus 1 times n plus 2 times x to the n plus 1 minus 1. So n plus 1 minus 1 is just n over n plus 1 squared times 6 to the n plus 1, which I can write as 6 to the n times 6. That is a sub n plus 1, or rather, if I call this now b sub n, maybe I should call it b sub n plus 1. And then now I'm going to divide it by b sub n, which is the same as multiplying by its reciprocal. So I'm going to have n squared on top, 6 to the n on top, over n times n plus 1 times x to the n minus 1, which I can, again, if I wanted to, I could write this as x to the, could write that as x to the n times x to the negative 1, which is x on the numerator here. Okay. I believe that should be good. So now it's just a bunch of, I apologize, I realize how messy this is getting. Hopefully you're able to follow. The 6 to the n's are going to cancel. X to the n is going to cancel. Let's see. What else happens? Oh, wait, did I use the wrong function? I think I used the wrong function, didn't I? No, I think I used the right function. Did I? Yeah, no, I'm doing things that I think I'm doing it. Okay. Yeah. Okay. So what else? Is there anything else? Yeah, n plus 1 can cancel. So then this equals x can come out times the limit Is that really the absolute value of x times the limit as n approaches infinity of um yeah, I really hope I'm doing this correctly. I have a habit of making silly mistakes. N squared times n plus oh, one of these n's could have canceled actually. N could have canceled there. So that I'm gonna redo this problem just because it's turning into a mess and I really need to make sure I'm doing this properly. I'm not comfortable with what I'm doing down here. So let me just redo this problem. Um, yeah, let me just rewrite everything on the next page where we have a little bit more space. So we have f prime of x equals the sum from n equals 1 to infinity of n times n plus 1 times x to the n minus 1 over n squared 6 to the n. Okay, so for ratio test, we're going to take the limit as n approaches infinity of the absolute value of 1 plus what I have. So n plus 1, n plus 2, x to the n plus 1 minus 1, which is just x to the n, over n plus 1 squared times 6 to the n plus 1, which is 6 to the n times 6. And then I'm going to divide it over the current term, which is the same as multiplying by its reciprocal, which is n squared, 6 to the n. And on the bottom, I have n times n plus 1 times x to the n minus 1, but I can just write that as x to the n and x on the top. Good. All right. Much cleaner now. This n plus 1 is going to cancel with this n plus 1. One of these n's is going to cancel with one of these n's. 6 to the n's are going to cancel. And then x to the n is going to cancel with this x to the n. Good. So now I can pull out absolute value of x. I have the limit as n approaches infinity of the absolute value of n times n plus 2 on the top, right? This n here, this n plus 2 on the top, over 6 times n plus 1 squared. Okay, and of course, as this approaches infinity, what happens? Well, we see that we have an n squared leading term here, and we have a 6n squared leading term here. So this is going to approach, this limit is going to approach 1/6, right, as n approaches infinity. So that means we have 1/6 times the absolute value of x. And we know that this has to be, by the ratio test, right, just like in a geometric series, the ratio has to be less than 1. So that means that our absolute value of x must be less than 6. Therefore, our radius of convergence is 6. Again, I really hope I haven't made a mistake. If I have, please do let me know. All right, and then we have g of x equals this. And just more ratio tests. They really want you to use ratio tests here. So now, I don't know if this has any relation to what we're currently doing. Somewhat, yeah, a little bit similar. And we're just going to do ratio test again on this to determine the radius of convergence for this Maclaurin series. So we have, let me write it out here. G of x is equal to the sum of what? N plus 1, x to the 2n. Then on the bottom, we have n squared times 3 to the n, right? Yeah, we have n squared, 3 to the n on the bottom. All right. So we're going to take, what do we have? We have the limit as n approaches infinity of, on the top, we're going to do n plus 2, because it's n plus 1 plus 1, times x to the 2n plus 2. Be very careful, because the 2 will, if I substitute n plus 1 where n is sitting, now have 2 times the quantity n plus 1, which is 2n plus 2. So I'm going to rewrite this as x to the 2n times x squared, because it's x to the 2n plus 2. And on the bottom, I'm going to have n plus 1 squared times 3 to the n plus 1, which is 3 to the n times 3. And then, of course, I can divide by the current term, which is the same as multiplying by the reciprocal of the current term. On the top, I'm going to have n squared, and I'm going to have 3 to the n. On the bottom, I'm going to have n plus 1 times x to the 2n. Good. Okay. So same thing, we're going to have a lot of cancellation, which is nice. X to the 2n cancels with this x to the 2n. 3 to the n cancels with this 3 to the n. And then I think that's about as much we can cancel. We can pull out our x squared. And x squared is always positive, so I don't need the absolute value sign anymore. I get x squared times the limit as n approaches infinity of n squared times n plus 2 over n plus 1 cubed, actually, times 3. Cool. So then, of course, we know that as n approaches infinity, we look at the highest leading terms, n cubed, n cubed. So we're going to approach this, this expression is going to approach 1/3 as n tends to infinity. So we're going to have 1/3 x squared, which of course has to be less than 1, which means x squared is less than 3. And here is where I'm not sure. I seem to have forgotten. Would I have to take the square root to find the radius of convergence? Yeah, I don't remember entirely what happens at this point. See, because I don't think the radius of convergence would be 3. I think what you'd have to do, you'd have to take the square root, right? Because if x squared is less than 3, that means x is actually between the square root of 3 and the square root of -3, of course, barring the endpoints, because the endpoints you'd have to do a different test. Yeah, I think this is what you'd have to do. And therefore, the radius of convergence, I think, would actually be square root of 3. Again, if I'm doing something wrong, please do let me know. Because as you can see, the center is 0, and the upper and lower limits are -√3 and +√3. So I think the radius would be square root of 3 and not just 3. Okay, I think that's it for the AP Calculus BC 2024 FRQs. Again, these are not the official answers. These are just my attempt, which means that it is entirely possible that I've made some mistakes here. And in that event, please do comment, let me know, so that others who are also trying to learn from this don't mess up. Okay, that's it. Thanks for watching.